So good afternoon. So today we are starting to look inside one of the basic parts of this course, that is the root lookup or IP address lookup. I have already set out the doodle for the group formation. I've seen that there is activity, so you are working to form the groups. Maybe we can discuss any issues about the groups. Today is too early because just set out the doodle, but during the next week. And next week I think we have regular lessons, and then there is we will lose a Wednesday for the 1st of November. But then on November 3rd is Friday, so I have to do lessons also on November 3rd because we are very short in time, so I cannot skip the lessons. Okay, so let's start. So this is the part of the course dedicated to algorithm. We will see the algorithm for IP address lookup, and later the algorithm for packet classification. And in the projects you will be implementing some of these algorithms, so you have to understand quite well how they work. And all these algorithms are characterized by the rules, obviously, but also some evaluation parameters by which we can compare one algorithm with the other. And so the parameters that we use to measure the performance are the following one. The first three are the most important. The first one is the lookup speed. Okay. Now we are talking about the algorithm for IP address lookup, so it means those methods that allow us to take the destination address for an incoming packet inside the router and start looking into the routing table to find the longest prefix matching, the longest prefix that is matching that destination address in order to forward the packet to the correct destination. So the lookup speed is the speed by which this operation is done, the time that it takes from when we start with the IP address or the destination IP address until the lookup operation returns what is the next address to forward the packet. And if you take, for example, an interface at 10 gigabit per second, most of the packets in internet packets have variable sizes, but most of the packets are short. So, for example, 40 byte in length, that means almost all is a header and very few information carried. So these packets from an interface at 10 gigabit per second arrive at the router by 31 million per second. So you have 31 million per second packet per second that are coming. It means that you have to perform 31 million lookup operation in 1 second. That means the time for each lookup operation is less than 30 nanoseconds, which is very demanding. So the lookup speed is very important. And of course you have to go so fast in order to keep the pace, to keep the matching with the line rate. Storage requirement is another important issue. The storage requirement is the memory that you need not to store the routing table, because that is basically independent of the algorithm, but to store the data structure that you have to build in order to operate the algorithm. And we will see that each of these algorithms has a particular data structure. And the storage is important not really in terms of the quantity of memory, because the cost of a single memory cell is really very small. But the problem is that the more memory you occupy, the more storage you need, the higher becomes the time to access into this memory. So if you have a very large data structure, then this has a negative impact on the speed that you need to look up into this data structure. So of course, the less memory is required, the better. And then finally, update time. The lookup tables are not static; they are always evolving, because the routing protocols are always running, and so the routing protocols, as you know, are changing the lookup table, or in case of SDN, the controller is changing the lookup table. And it has been estimated that, for example, for a big BGP router, which is a router in the core of the network, the rate of updating can be up as high as hundreds of updates per second. So the update rate must support must be over 1,000 updates per second in order to be to have some margin. And each time the lookup table changes, then you have to change also the data structure that the algorithm is using in order to represent this lookup table. So this is very important. And for these three parameters, lookup speed, storage requirement, and update time, we will also give upper bounds for each of the algorithms. So each of the algorithms that we will see will be characterized in this by these parameters. Then there are also other parameters, for example, the scalability, the size of the routing tables is quite large, but it is also increasing year after year. It has been estimated, for example, that each year the large tables, routing tables in the core of internet, they grow by 25,000 new entries for each year. So this algorithm must be able also to operate on a very large amount of data. Flexibility implementation, we will basically look at two different classes of algorithm. One class that is implementable in hardware, so by hardware, and the other class of algorithm implementable by software. Clearly, in both cases, you have pros and cons. A hardware implementation tends to be faster, but sometimes more expensive. Software implementation is more flexible, but slower. And then also in the field of hardware implementations, there are some algorithms that can be implemented using application-specific integrated circuits, ASICs, which tends to be very expensive because they have to be customized for that specific algorithm, or network processor or generic processor. So, in any case, in quantitative terms, we will focus on only the first three parameters. Okay. So let's start with this set of algorithms, that allows the lookup operation, and these are all algorithms that have to be implemented using software. Okay, it may be some hardware implementation, but the usual implementation is by software. And they are many of them. There are many of them. We will not go through all of them. In particular, we will skip the Nube algorithm and the trie algorithm because they are too complicated. But we will focus on the first group that is based. You see the word trie, that is trie or trie, that is appeared the types. So this is based on the tree structure. And then the final two, the binary search on prefix length and binary search on prefix ranges, which use very different structures, but data structures, but they are interesting and instructive. So we can start with the first group that is composed by the trie algorithm. The simplest one is called the binary trie or binary tree. This word trie actually is a special term that comes from retrieval. This was invented by Frederick, introduced by Frederick, and he pronounced it originally as a tree, but since the trie is not exactly a tree, it's a specialized tree, some other authors want to pronounce it a trie, so the trie is more particular and also reflects the fact that the word is not written as a tree but is written as trie. What is a trie? In this case, a binary trie, also called a unibit trie, is a representation based on the binary tree, obviously. So you have a set of nodes, it's a graph. You have a set of nodes and a set of edges, and each node is connected by the other node by an edge. And each node is actually a data structure that is linked in this way. So you have in every node a field that is used to contain an information, so data, and then two pointers that connect this node to the other node. What kind of information you have to store there? You may store the next hop information. So to understand how we can build this data structure, we have first to start from the routing table. Okay, so in all these algorithms, the first step is to build the data structure that is used by the algorithm, starting from the routing table. We have seen routing tables represented ways that are very similar to the real implementation, but for the sake of simplicity, in this this algorithm, we will always write the routing table in this way. So you have a set of entries. Each entry has a label, P1, P2, P3, P4, P5, and so forth. This label is also a symbolic way to mean a next hop information. So here P1 stands for next hop information, where you have the address of the next hop router. Okay. But we don't write all the IP address, we write only P1 for short. And then you have the prefixes, network prefixes, and we will write them with a wildcard. So you have basically the prefix, for example, in this case, P7 is 11101 and then the wildcard. It means that is a network prefix of length 5, so that mask is of length 5, has 5 ones and the rest zeros. And written this way, it means that here you are referring to the whole block of addresses that goes from 11101 0000 until 32 bits up to 11101 and then 1111 until 32 bits. Okay, so it's a way to represent for short a block of addresses. So then in some cases it's useful also to sort this routing table in order of increasing prefix length, like in this case. So you have on the top, where you have the wildcard, that is, as you know, as you probably surely know, refers to the what? How do you call it? This entry in a routing table. The default router. So that entry that matches always with any packet that is coming, but is of the minimum length possible. So you go there only if you don't have any other more specific entry that is matching. Okay. Then, what is the rule in order to build the binary trie? We start from the routing table, and then we start scanning the routing table from the shorter prefix, that is, in our case, wildcard. So here immediately we have the wildcard with a specific information, which is next for proving. So this becomes the first node, that is the root node of the file. Okay. In this case, in this node, we will, in order to implement this data structure, if I draw a node on the paper, it means that I have reserved part of a memory location for this data structure. So next of information, left pointer and right pointer. And in this case, we also write P1 as in the information field. Okay. When we have to write something in the information field in a node of this type, we use the gray color in order to mark that in that node we have some information. So this node is gray and it is labeled with P1. It means that in that node you have to store the next of information of the default router, the address of the default router. Then we have to, so we have defined what we put inside. Now we have to define what we have to put in the pointers, so in the two fields of the pointers. And we have to take a convention so that when we start from the router, we move down. If we want to follow a path where we have a 1, let's say the first bit that we consider is a 1, we go right. If the first bit we consider is a 0, we go left. Okay. So this is a conventional. You can, of course, do other way around. The important thing is that once you decide for a convention, you keep consistency where you're building the code. So a 0 corresponds to a left arc and 1 corresponds to a right arc. And so after the first node, that is the root, we start inspecting the content of the prefix database, considering a length of only 1 bit. Okay? And so here, if you look at the prefix database, the routing table, we have entries with 1 and also entries with 0. So we have entries both with 1 and both with 0. So it means that we have to instantiate one node here and also one node there. Okay. So 0 and 1 are both connected to some other nodes. Or, if you want to say it another way, this root node will have two children, one on the left and one on the right. So let's look at again at the database. Since we need both the arcs or the edges, then we have to append the nodes. an edge is always on the picture if you have a node to append it. And then if you inspect here all the prefixes, you find that there is one prefix of length 1, one that is one bit long. All the other prefixes are longer. Okay. This prefix that is of length 1 starts with the 1, so the first bit is the 1. So it means that in the node that is here, that is connected to the right of the first node, we have to write some content that is the next hop indication of that node, of that prefix, P2. So that node will be gray as the root. On the other side, on the left, all the prefixes that start with a 0, that is this one, P3, are longer than 1 bit. So P3 is longer than 1 bit. Okay. So here we don't have to write anything in the content field because there is no prefix that is 1 bit long, which the first bit is 0 that terminates there. So that node will be white. Okay. So we have to add a white node when the node does not correspond to a prefix in the database entry. This node here corresponds only to a piece of a prefix, but not to a full prefix. So it remains white. Instead, on the other side, the node on the right corresponds to P2, which is a full prefix. So it's gray. Then you go one step further. One step further means that you go down one level in the tree and you go on the right side in the inspection of the bits of the prefix database. And here what you find. Okay, so now we have two nodes, one white and one gray. These two nodes may have children or may not. In this case, for example, if you take the left node that is 0, here you have only one prefix that was started with 0 as the first bit, and then continues with another 0. So from this node, you just have to instantiate one child. Okay? And it will be the left child because you have another 0. And the node that you put here below is gray because it corresponds to a prefix in the database P3. On the other side, if you look at P2, you have several prefixes that started with 1 as a first bit, and they continue both with 0 and also with 1. So you have to instantiate the two children. On this side, none of the prefixes stops at 2 bits. Okay, so these two nodes will be both white. And then the procedure is iterated, so you continue. Here you notice that no arc is created because you don't have an entry that corresponds to that bit sequence. You don't have any entry corresponding to 0, 1 sequence, so you don't create any arc. And you iterate the procedure. Next level, you find other prefixes. You need here you don't need any left child. Here you need a gray node. On the other side, a white node. Notice that you cannot put in the graph a white node with no child. Okay? Because if you have a white node with no children, that node is useless, so you have to remove it. The white node stays in the graph only if it has at least one child.
So that's why this is not a white node?
not that P3, yeah, exactly. P3 is a great node, so it should be very much to repeat the database. P3 must be gray because it corresponds to a full prefix. Okay. 00 is a prefix that is an entry here. So here you need to store information about next door. Okay. But if you if you would have nothing on this side, here you cannot put the white node. For example, this white node is only temporary. If there is nothing on the next level, it will be removed. Since a white node is present in the tree only if it has at least one child, as a consequence, only gray nodes can be the leaves of the tree. Okay, so a gray node can be an intermediate node, or it can be a leaf. For example, this is a leaf because after this entry 00, you don't have any other prefix that continues that starts with 00. So this is a leaf. The white node is always an intermediate node. It cannot never be a leaf of the tree. So here we go on. On this part we stop. Here we find another node P6, P5. Then we go on another level. These are the nodes that are added. Another step again. And this is the last. Okay. The last node that is added is this P9. And the procedure stops when we have inspected the longest prefix that is in the table. And the number of levels that we have in the tree, the final number of levels that we have in the tree, is equal to the number of bits of the longest prefix. In this case, we have seven levels. 1, 2, 3, 4, 5, 6, 7, because the longest prefix has 7 bits. Okay. Actually, the number of nodes that you can count from the top to the bottom is 7 plus 1, because we have 3. But the number of levels, which corresponds to the number of edges on the longest path, is exactly equal to the number of bits of the longest prefix. So gray nodes can be labeled when the nodes can be gray and labeled when they correspond to an entry in the prefix database. The white node must always have at least one child. So this is the rule in order to build this data structure. And then how do we use this representation in order to perform the lookup operation? This is very simple. When we take the destination address out of the header of the incoming packet, destination address is a sequence of bits. Okay? It's a sequence of always of 32 bits. If you start from the root, this sequence is actually defines actually a path in the tree. Okay? So the sequence corresponds to a specific path and a single path in the binary trie. So in order to make the lookup operation, you just take the prefix and start the destination address and you start reading it bit by bit, and you start moving in a corresponding way on the binary type. So starting from the root, if the first bit is a 1, you go to the left, right. If the second bit is a 1, you go to the right, and so on. And here, for example, you have 1, 1, 1, 0, 1, 0, 0, 0, and so on. This means that you describe this path in red. So 1, 1, 1, 0, 1. Okay. So what is the goal of describing this path? The goal is to find, to reach gray nodes, and to reach the gray node that is on the lowest level possible. So basically, it's first step search into the tree. In this case, taking this destination address and following this path, you arrive to the node P7. Okay. So the result of the lookup operation inside the routing table will be P7. This is the next node. And this is also the result of the longest prefix matching rule applied to this routing table using this destination address. Okay. That is the longest prefix matching. You have to notice that along the path we also crossed not only P7 but also other gray nodes. The gray nodes that have been crossed are matching entries of the routing table, but these prefixes are not the longest one. They are matching, but not the longest. The longest is P7 in this case. In any case, while you are exploiting this procedure to make the lookup operation, there must be somewhere a temporary register where you store all the prefixes that have been encountered. Basically, not all, but the last one. So, starting from the top, the first prefix that is corresponding to a crossed gray node is P1. So, in this temporary register, you will write P1. Then the second is P2. So, you can delete P1 and write P2. The third is P5, delete P2 and write P5. The last one is P7, and that is the final result. Okay. Why you can forget about previous prefixes that have been crossed? Because when you find matching here, this is the shortest possible matching prefix that is matching. If you find another prefix that is matching along the path, but going down one level, this will be surely longer than the first one. Okay. So you can forget about the first one. Sometimes it may happen, this situation, this is another destination address on the same field. If you map it as a path on the field, you see that it's 1, 1, 1, so you cross P1, P2, P5. Then there is 0, 0, and then there is another 0. So you go down here, and then you should go on the left. Okay, but here you don't have any node. So it means that you cannot go any further. This path cannot continue, and so you have to backtrack to the last node that has been visited. So the final result of this second lookup would be P5. Okay. This is the longest prefix match. This is why you have to keep this temporary register where you register the last node that has been visited. Because it may happen that you cannot continue until you find a leaf. In this case, you don't reach any leaf on the tree, so you have to backtrack and take the first ancestor that you have visited. Okay. That is the longest prefix matching. This operation is called backtracking. Questions? Yes.
If a user backtracking, how can see that there isn't an error and there is it isn't the real destination? If I have, for example, I have a prefix long, for example, 4, 3, 1.
1, 2, 3. Yeah. Okay.
Is fine or it isn't good?
No, if you have 1, 1, 1, and then another 1, you have to stop here. Okay. So in this case, you will find the solution. That is the last node that has been visited. It is not the leaf. Okay. So you cannot say that you need the backtracking, but you have to stop. Always remember that we write only the first bits of the destination address, but all the destination addresses contains 32 bits. Okay. The fact that we write only the first bit is only because we have a tree of a limited depth. But so you at a certain point when you don't find any more possibility of going down, you have to stop. But in the destination address, all the destination addresses are 32-bit long, so you cannot predict from the destination address what is the size of the matching prefix. Okay. So now we have seen how to build this data structure, how to perform the lookup operation. Then we have also to specify how we can modify the data structure when the routing table changes. Basically, this is always the most complicated operation from the logical point of view. So we will see it in a detailed way only for this case, that is the simple binary trie case. For the other case, it's more not specified exactly. So what happens if we have to modify the tree that is being already built according to a certain routing table, because the routing table changes. The routing table may change in two ways. A new entry is added, so we have to specify a new prefix, or a prefix is removed from the routing table. Okay? So in the first case, if you have to a new prefix, for example, this 10111 star, how do you have to modify the binary tree? First, you have to go down according to the new prefix as much as you can, and this refers to the previous example, so 10111. Is here 10111. So in this case, you go down, and there can be two situations. There is no pointer for that prefix, so in that case, you have to add the pointer and then maybe add another pointer until you build the whole path that is corresponding to the prefix. Then you will place at the end a node, a gray node, where you write the information of the prefix. Otherwise, you can find that the node already exists for that prefix. It's a white node, so you simply mark it with a label. So the node becomes from white to gray. This is 1 1 0 1. Okay. So imagine here this is a gray node, obviously. This is also gray. So it means that here you have a prefix. The prefix is star, then the prefix 1 star, and then the prefix 1 1 0 1 star. Okay. So now you add the prefix 1 1 star. 1 1 star. Here you have already a white node. This will become gray. It's very simple. Then you want to add the prefix 1 1 0 star, 1 1 1 star. Say 1 1 0 star. So you start from the top 1 1. You are moving on the existing tree. Then there is another one. Here you don't have anything, so you have to add an arc with a node, and then you have you don't stop, you have a 0. So you go down here, you have to add another arc, another node, and this will be the prefix that you have. Okay. For the dilation of a prefix root, for example, you want to remove this new entry here, or this one. Okay. This is removed. Again, you have to go down, following the path that corresponds to the prefix. Here you have a gray node, but this gray node has one children. Okay, so you have to remove the prefix by setting this node to white, but you cannot take out the node because the node is attached to other prefixes. Otherwise, if you want, for example, to remove this prefix here, okay, so you go down 1 1 0 1. Here you have the prefix, you want to remove it. You take off this node because it has no children. Then this is a white node. White node cannot exist without any children. It has no children. You take off also the white node. Okay. This is a gray node. You cannot take it off. So this is basically the operation that allows you to modify the binary trie according to the modifications of the routing table. Okay. Performance. So we have these 3 parameters: lookup complexity, storage complexity, update complexity. In order to simplify the evaluation of this algorithm, we always try to relate these parameters to the dimension of the problem, which in our case is given by the number of prefixes that you have in the table, which is capital N, and capital W, that is the maximum length in bit of the prefixes. So the prefix of having the maximum length. And we use this big O notation. Okay? Big O notation is useful to assign upper bounds. The formal definition of big O is this one. So if you have a function g and a function f, this function f belongs to the large O of g if there is a certain value of x, that is the argument of the 2 functions, x sub 0, and a certain number n, which is a multiplier greater than 0, so that when x gets larger than x sub 0, so beyond this threshold, and start growing, then it is always true that f module, f as a function of x module, is smaller than n multiplied by g as a function of x. Okay, so this function g is an upper bound to f. It is not necessarily the tighter upper bound possible. Maybe you find another function that is smaller, so bounded by g, but it is able to bound f. So in this case, you have found a tighter upper bound. But still, we are happy if we find an upper bound, even if it is not the best possible, the tightest possible, because in this way we can compare different algorithms. If you are able to find these simple expressions, then it's very nice. If you want to make a very a more careful analysis, you may find some tighter bounds, but they are much more complicated. Okay. So in the case of the binary trie, the lookup complexity is bounded by W, where W is the depth of the tree, the distance in hope from the deepest leaf to the root, or from the root to the deepest leaf, or also the number of levels of the tree. And the maximum number of nodes that you find on the path, as I already said, is W plus 1, because you have to count the root node. Okay. So in this case, you have that the lookup operation is bounded by W. Storage complexity is bounded by n multiplied by W, and the update complexity goes like the lookup operation. The reason why the lookup complexity is big O of W is very simple, because each time you have to make the lookup operation, you have basically to follow a path along the tree, and the longest possible path is composed of W steps, okay, W arcs. The storage complexity is more complicated, we will see in a minute. And the lookup complexity is an O of W should be compared with the complexity of the linear search. Okay. The linear search is the operation that we do manually when we have a routing table. That means that we take as we have done in previous lessons, we take the destination IP address, and we start matching it with the first entry, then with the second, with the third, and so on. Since this routing table has n entries, this is a linear search, and the complexity is a big O of n. If you sort the entries in order of prefix length, as somebody suggested, maybe you can improve this operation, but still the complexity is O, big O of n. What is the advantage? As we've said, W, the maximum value of W is 32. Okay. Actually, usually, since here you store not IP addresses but network prefixes, you never have a network prefix of 32, because as you know, you cannot create a network with only one address. You need at least 4 addresses. So this is in the most of the cases less than 32. N is on the order of several thousands, okay, or even hundreds of thousands of entries. So this is much more efficient in terms of lookup complexity than the linear search. The storage complexity is W by N. This is not so intuitive. The explanation is the one that you can see in this picture. You have always to consider that the worst case is when you have all the gray nodes at the bottom layer. So it means that you have n prefixes. All the prefixes have the length w, so have the maximum length. Okay? So it means that you have long chains of white nodes, and here you have the gray nodes that are appended below. So there is all these parts that is basically a rectangle that is roughly the size of W by N. In this case, the unit by which you measure memory occupation is the node. So the number of nodes in this graph is roughly W by N. It's not exactly W by N because you have some levels that are used for the tree, so to connect all these long branches. Okay? But if you have n nodes here, that means you have n branches, that part that is a tree contains n minus 1 nodes. Okay. If you compare n minus 1 with w by n, this is much larger. So you can neglect this part while you are counting the complexity and consider only this part that is the largest part. So this is why the complexity is O W by N. Okay. So basically N is large, but usually the number of stages that you have to use to interconnect all the branches is typically less than W because it is the logarithm of base 2 of N. Okay, so it's more. Yes.
How often the prefix then gets changed? Like whenever you configure a /30 subnet, then or
The prefix length?
Yeah, how often does it get changed?
It's the same rate as you modify the routing table. When you have modifications of the routing table, you don't know what is the new entry. For example, because you add a new entry, it may be of any length. Okay. Statistically, however, as we will see later on, most of the prefixes in large routers are shorter than 24. Okay, are shorter than 24 bits. It's more difficult that you set up a prefix that is longer than 24. This is not used in this case, but it will be used in other implementations. So this is the basic binary trie. Then we have now some, let's say, modified versions. Modified versions in order to exploit specific properties. And the first one, that is very easy to understand, is the so-called complete binary trie. So the basic binary trie is not complete because you have branches of different length, as you can see here. The complete binary trie is instead when you have a number of levels, a number of nodes in the bottom level, so a number of leaves that is equal to 2 to the W, where W is the depth of this trie. So you have basically the complete tree. Where W is the longest prefix that you have in the routing table. Here you find you see a routing table. It's a little bit small, but you can see that whole. In this routing table, the longest prefix is B, is 5 bit long. So it means that if you want to build the complete binary trie related to that routing table, you will need 2 to the 5 nodes in the bottom layer and 5 levels. It means 32 nodes in the bottom layer. And here you see that this is the construction of the complete binary trie, and A, B, C, D, and D, F, G, H, and I refers to the gray nodes that you have to put in order to represent that prefixes. But the complete binary trie is only useful for a specific purpose, that is to have all the nodes, all the gray nodes in the bottom layer. So once we build the complete binary trie, we do it not to have the gray nodes in the intermediate layer, but to have them all at the bottom layer. And so what happens when we want to move all the gray nodes in the bottom layer? It may happen that we have a gray node that is already in the bottom layer, like for example B, that is the longest prefix, is already here. So we don't have to change anything. But in other cases, we have nodes, gray nodes in the intermediate levels. For instance, A and C. Let's look only on the left side of the tree. So we have to project these gray nodes into the bottom level, and the rule is that a gray node in the bottom level will inherit the prefix of the closest ancestor gray node. Okay. So for example, the node that is here has the closest ancestor that is gray. Here is C. Okay. So we can write the content of C in the bottom layer. A node that is here, if you follow up the path until towards the root, you will find that the gray ancestor is A. The closest gray ancestor is A. So the node that is here will inherit the content of A. Okay. The previous node, the node that is in this place, so on the right, has two ancestors actually. One is C and the other one is A. But the closest is C, so it will inherit only the content of C. All the other nodes, once we have done this operation that is called also leaf pushing, all the other nodes will be turned into 1. Okay. There is an equivalent way to define this procedure that is a little bit more practical. That is the following. Now let's focus on the right half of the complete binary trie. Here we have the nodes E, D, F, G, H, and I. That are gray nodes in the intermediate position. We want to perform the same operation as we have done before. So this practical procedure is the following. First, go to the level. So we have the level W. The level W, if there are gray nodes that are already here, they will stay here. Then we go up one level, so in the level W minus 1 in this case. Here, if you have gray nodes, you have to copy the content to each bottom leaf if the descendant is still empty. For example, here F has two descendants, two children, they are both white, so we can copy the content of F down. The same for G, the same for H, the same for I. Okay. And this node will turn gray, the original node will turn white. Okay. Now we go up another level, and we are here at the second level, intermediate level, and we repeat the same. So here you find only one gray node, which is E. the descendants of E in the bottom layer are these 4 nodes. They are all white, so I can copy the content of E in these 4 nodes, and E is turned white. Then I go up another level. Here I don't have any gray nodes. I go up, there is D, that is the gray node, and so you have to look at the bottom level. Here we have still 4 nodes that are white. I copy the content of D in the 4 nodes. They turn gray and D turns white. Okay. And then there are no other gray nodes in the tree. So you can say it this way, or in the other way, it's the same. The second definition is more practical if you want to implement an algorithm that do it automatically. So why we need all this complex procedure and we want all the gray nodes in the bottom layer? This is it comes the advantage of the complete binary trie. So now we have the bottom leaves that are all gray, and each leaf has a content, and all the leaves can be sorted from one side to another, so you can make them corresponding to a number. You can just number the bottom leaves from one direction to another. The first one is 0, the second is 1, the third is 2, and so on and so forth. And since we are reasoning as machines, the best thing is to write these numbers in the binary form. Okay. So now each entry stores the result of a longest prefix matching operation that corresponds to a specific memory location. Because now all these leaves that are at the bottom can be stored in an array, and you have also the address of all the positions in the array. Okay. This allows us, again, to perform the lookup operation with a single direct memory access. So when we want to, for example, perform a lookup operation for this incoming packet that starts with 0, 0, 0, 0, and go on, this corresponds to the path in the complete binary trie that you see above. But this path will always end to one of the bottom leaves where you find the information. Okay. It means that it will always end to one of the cells of this array. And you know in advance also the address of that cell. In this case, the address is 0, 0, 0. So the longest prefix matching operation turns the result. If we want to use the tree, we have to follow the path, but we can directly access the memory using the received first bits of the destination address as the key, as the address. Okay. And here we find directly the result. So actually we need only this, the tree to make the construction, to build the database. But then for the lookup operation, we can forget about the tree. We have a direct memory access. This is another example, 0, 1, 0, 0, 0. This is the path, and this is the result that you find with the direct memory access. Going to using these first bits to as an address to look into the memory. This is another example, and so on. Okay. So this is a big advantage in terms of the complexity of the lookup operation, because if you do it with direct access, what is the complexity is a big O of 1. 1 means one single access. The drawback is the storage complexity. Now you need always an array that contains 2 rise to W positions. So you have to know in advance what is the maximum length of the prefixes that you have in the table, and according to that maximum length, you have to create this array. So if you consider that W is 5, like in this case, okay, you have 32 positions, no problem. But if you consider W24, you have 2 to the 24 positions, which is not so easy. It's a large memory. So there are some advantages and drawbacks as usual, but the lookup complexity is very important, and is, in this case is very fast. So this is basically the complete binary tree. Now there is another case that is the disjoint binary tree, that is something in between. Okay. And it's a compromise. It is better than the binary trie, the original binary trie, because you can avoid the use of backtracking, and in terms of memory occupation is similar to the binary trie. What is the procedure in order to build a disjoint prefix binary tree? The condition is that it represents a set of disjoint prefixes that have all the prefixes at the leaves. So again, we have to move the gray nodes to the leaves, but not necessary to the leaves of the bottom layer. Okay. So there is the tree is not complete, it's not full, but all the gray nodes are leaves and not intermediate nodes. So that no address prefix is a prefix of another. And so it means also that all the paths that we will draw into the tree while doing the lookup operation will always end to a leaf. Not it will never stop before reaching a leaf. And the technique is that we have to add the leaves to the nodes that have only one child. This is called also leaf pushing. So these leaves that we have to create in order to transform the basic trie into the disjoint binary trie will become gray if the ancestor taking the properties of the closest ancestor. So we have to perform an operation that is similar to the previous one. This is an example that is always more clear than the description. So we have to perform a leaf pushing. We start, this is the original binary tree, and this is the database, the prefix database. We start from the bottom levels. In this case, for example, the bottom level here is P9. The P9 is here. Okay. Then if you take the part of the tree, the original tree that goes from P9 to P6, that is the closest ancestor, you notice that you have a white node with just one child, another white node with just one child, and the gray node P6 again with one child. So the first operation is to introduce the missing children. So you have to add one here from P6, the other one here, and the other one to the other white node. And then we copy in these newly added nodes the content of the ancestor. In this case, it's P6. For all the nodes except the P9, where we have already the gray node. Then you go to the other branch of the tree, and we do the same. Here we have P8 and P7, and the ancestor is P5. P5 has one node that is one child that is missing, and also the white node before P9. So we are adding all the children that are missing, and copying the content of the ancestor that is P5. Then you iterate the procedure, and the result is this tree. Okay. This is the disjoint prefix binary. Here you can see also that we can write the same by transforming the routing tables in this way. That is basically mapping all the entries to longer entries. What happens when we have to perform the lookup operation? That is, for example, a lookup for the first green address that is being received, 101010. You see that we go to the P4. This is the path of the disjoint binary trie, and on the left, top left, you find the equivalent path on the original binary trie. So in this case, there is no difference. In this case, the red one, we have a difference because here in the original binary trie, we have to backtrack into P6. In this case, we find immediately the result because P6 is copied here at the bottom. And then there is this blue example that is here. Okay. So we have eliminated the need of performing backtracking in the binary. Okay, I have to stop here because I have another appointment immediately. So we will continue on Friday with these techniques. Okay.